Okay, so we're going to look at our bivariate and multivariate regression models. For starters, we need to understand what regression is. So regression is a statistical tool used to describe and predict data. So data gathered for research purposes contains predictors, sometimes many predictors and outcomes. Regression is going to allow us to analyze the relationship between these variables. This can be really simple or it can be very complex. To simplify this, when we have one variable and we want to calculate its outcome, the best guess will be the mean. But the mean isn't always very informative, so we can use predictors to better predict the outcome. For example, the level of education a person has could give us an idea as to that person's salary bracket in the future. We assume there's a positive relationship between education level and salary, so this can give us a hint. We assume that this will give us a hint as to how much money this person will make. So education level here would be the predictor in the situation. However, a single predictor oftentimes doesn't do a great job at predicting the outcome, so we're going to need multiple. Robert Abelson's 1985 variance paradox article showed us that one individual predictor, like an individual player's batting average, doesn't always help us guess the success of the team due to the fact that in order to win a game, multiple players need to have a high batting average as well. It's just one piece of the puzzle, and it requires us to take a look at other predictors in order to understand and predict if a team is going to have a high success rate. Regression is based on the ordinary least squares principle. This method finds a simple linear regression of data, meaning it models a linear relationship between one or more variables. So looking at BMI, we're going to try to look at some factors that might affect our BMI and that we can use to calculate and predict whether someone will have a healthy BMI or not. So our Y variable is going to be our BMI, and our first predictor is going to be parental BMI. So there are some research studies that suggest that parental BMI has a strong positive correlation with somebody's own BMI. The larger the BMI of your parents, the more likely that yours will also be high. So we assume this is going to be a positive predictor, or that they're going to have a positive correlation. So we want to make sure that these predictors are orthogonal. So we'll do some diagnostic testing to figure that out. And we want to make sure that they pass the uh, assumptions, the regression assumptions. Um, we could also add other predictors, multiple predictors, which we'll do in the future soon enough. Something like socioeconomic status. But it's important to know that a lot of these predictors are going to have different scaling methods, and that requires standardization later on in order to be able to compare these predictors. So Schultz's 2010 article informs us that standardizing your beta coefficients is going to allow us to compare two different scales of measurement, which is what we're going to use. Um, so let's take a look at a quick plot, a little bivariate plot to understand the relationship between parental BMI and BMI. So we see, this here is line of best fit, um, indicating a positive correlation, a positive slope between parental BMI. So, the larger the BMI of your parents, the larger yours will be, most likely. Kind of like what we suspected would happen. So taking a more detailed look at the numbers is going to help us understand the relationship a little bit further. One of the first things we're going to look at is this intercept here. So what would happen if our y is at 0, essentially? Our estimate is going to be about 2.18. And then for every unit of change in BMI, we expect a 1.1 increase in parental BMI. Or it's about 1.05, but I'm just rounding it to 1.1. And just using some of these basic parameters, I can create here a bivariate regression equation, which is going to look like this. We've got our BMI is going to equal, so our y variable is going to equal 1.1, which we got from here, times x, which is our parental BMI, which is our predictor, plus 2.2, which is our y-intercept. or where the y-intercept starts. So talking about these parameters a bit more, all of these parameters also have a standard error, which we see over here. This is going to indicate how different the population mean is from the sample mean. Gives us an idea of how much our mean is going to vary if we were to repeat the study with some new samples from the population. So the standard errors can be affected by a lot of different things, like sample size and multicollinearity are some big ones. Especially if we have multiple predictors. So using the standard error, we're able to calculate the t-values by taking the standard estimate, the estimate over here, and dividing it by the standard error, which is going to give us our t-values. That's 7.6 and 33, this was a bit high. Anyway, in this case, we're going to look at this p-value here. That's going to tell us if our predictor is statistically significant or not. In this case, it is. It is like smaller than the 0.05 kind of metric that we compare it against. And yeah, so we can reject the null in this case. So now we're gonna just kind of do a little rundown of these diagnostic plots for this bivariate model. We see some slight deviations here at the tails from our expected values, but it's still pretty close to the line. It appears relatively normal right over here. We've got some stuff at the tail end, but it's a minimal S-shaped curve. So I would say they're relatively normal. Our points seem to have like a pretty even distribution across the x-axis. It's a bit more plots. We do see an outlier that is potentially skewing our data. But if we look up here at the predicted and observed values and comparing the lines of best fit, we see that they are very close. But we do see that this data point right here might be affecting our data just slightly. And then a little histogram has a, really nice, normally distributed shape right here. So it looks like, parental BMI is a pretty good predictor. But just looking at one predictor isn't enough. It's important to look at multiple predictors, multivariate regression. It helps us account for shared variance amongst our predictors and our outcome variables. And this is a better example of real life. Rarely will you ever have a super isolated variable. There's always going to be multiple variables that are affecting an outcome. So Friedman's statistical models and shoe leather article kind of talks about using just a 3-variable approach and to statistics, and that can miss many other factors that make up our outcome. So as we'll see further on with our multivariate regression summary, we'll see that there's going to be multiple variables that are affecting our data, and some are statistically significant and some are not. Some really account for variance and some do not. So a 2-variable approach is just not enough to represent life. So we do a multivariate regression. So we've included more predictors, as you see here. I've included socioeconomic status, activity level, education, and these are just like the first 6 data points that I gathered. But this is definitely not the entirety of it. I just kind of wanted to give you an idea of what we're looking at. Okay. So we're going to look at the summary a little bit, kind of like we did earlier. So we'll just start off with the intercept. We'll see that we've noticed that the intercept changed very slightly. So it was about 2.18. Now it's about 2.21. So it's just a slight increase in our intercept. And the adjusted R-squares down here also changed slightly. It was about 0.852. Now it's about 0.853. So it's increased a little bit more. This is kind of telling us that 85.3% of our variance is explained by these predictors. This is actually very similar to our bivariate model, the parental BMI kind of explained pretty much the same amount, 85.2 something percent of the variance. So that was a pretty good predictor. Let's see, looking at our p-values, we see that parental BMI is the only statistically significant variable or predictor. Socioeconomic status and education are definitely not, and activity is kind of close, but it is not statistically significant at the O5 level. Some other calculations that we made was the variance inflation factor down here. So this can inform us about the shared covariance or multicollinearity amongst our predictors. We can see that parental BMI and activity levels have very high variance inflation factors, which indicates some multicollinearity. We can see here that the activity level, right over here, the activity level is not a statistically significant factor on its own, and it might be suffering from either collinearity or an outlier that might be influencing our data or something. So I did go ahead and plot activity level as a predictor on its own, and it turns out that on its own it is a significant predictor, so it's likely suffering from multicollinearity when grouped together with the parental BMI, since they both have some really high VIF factors or VIFs, and but parental BMI still is statistically significant. But for the sake of time, I'll leave that how it is. Another thing we can do when we have these VIF factors that are kind of high is look at the correlation matrix. So I've got it right over here, and we can see I've bolded it. Parental BMI and activity level have some really high correlations. They're highly correlated, these two variables. As we kind of suspected by looking at this. And I also ran some diagnostic plots for our model, our multivariate regression model. And we can see some kind of very similar kind of distribution here on the x-axis, a very subtle S-curve here, similar to the bivariate model. Same thing here, the observed versus the predicted lines are very, very similar. And the data point in the Cook's distance chart over here, we've got a value with a very large Cook's distance, which I just said, which means there's a lot of influence of the specific data point when performing least squares regression analysis. So it's possible that this data point over here is causing some of our factors, specifically something like activity level, to have such high VIF levels and not be statistically significant. And then the histogram is also evenly distributed. It looks pretty nice. Back to our summary. So there's some multicollinearity happening. Overall, it's not great. Our model is suffering from some multicollinearity, like I said, some high VIF values, indicating some collinearity, especially between parental BMI and activity level. And it's unfortunate because they both individually seem to be statistically significant when tested on their own. But parental BMI seems to be one of the better predictors. Our standard errors can be pretty inflated also because of this, our high VIF values and stuff. So there is some complications when you start adding multiple predictors, as we can see here. But our bivariate model with the parental BMI and BMI seems to be a really good predictor. But yeah, that is a summary of these regression, bivariate, and multivariate analyses. Thank you.